about our work in the ERC-funded group first, led by Raffaella Schneider. My name is Luca Graziani. I'm a postdoc in the group. And today, I'm going to show you our work based on different feedback mechanisms we are implementing in our theoretical models to constrain and to try to understand how star formation is regulated through cosmic times by feedback. And this is work done in collaboration with all people in our group here, with Stefania Salvadori in Paris, and people of the Benedetta Ciardi's group in Garching, Germany. Also, Daisuke Kawata in UCL in London is collaborating with us, providing n-body simulations. So I was trying to understand what feedback, how to introduce the feedback, and the classical scheme to discuss about feedback is just to classify the feedback among three different categories: radiative, chemical, and mechanical. And if you ask yourself, what is the interplay between these three mechanisms, you will always find a connection. Radiative feedback changes the physical status of the gas, for example, by ionization, heating, by affecting the environments in which dust can evolve, for example. But once you have a chemical feedback at play, you also change the type of radiative sources, moving from one generation of stars to the other, for example. And this changes the sources of your radiation field. And so you have a back effect from chemical to radiative. Same thing can be done from radiative to mechanical and from chemical to mechanical. So this is to show, even this is arbitrary and really personal, this is to show how complicated is this and how these three feedback mechanisms are at play when you consider the evolution of stars and quasars in the high redshift universe, especially in the high redshift universe. So basically what we learn is that feedback, especially in the high redshift universe, is highly nonlinear. Everything is connected with somebody else and poorly constrained by observations. The role of radiation sources is not clear at all. The chemistry is not fully understood. I mean, one example is this, grain growth. What is grain growth? We know, I will show you that we need this mechanism, but it's not totally clear from the atomic physics point of view. The wind models are implemented in many codes, but not totally, fully constrained. So to study this problem, you require multi-scale numerical simulations, because you also have that these three feedback mechanisms, they act at different scales. And multi-scale simulations, numerical simulations are required. So today, what I will show you is, we'll introduce you these three codes we are developing in our group: Crash, Dusty Gadget, and Gamesh, trying to solve not the entire problem, but a piece of the problem, trying to study what is the effect from radiation to the chemical status of the gas with Crash. What is the effect of mechanical feedback and chemical feedback in producing metals, spreading metals, producing dust, and spreading dust? And last work will be in showing what the Gamesh pipeline is doing, trying to implement radiative and chemical feedback at the same time and studying the interplay between these two mechanisms. So let's start from radiative to chemical and introduce this code, Crash. So Crash is a code developed mainly at MPA, Max Planck Institute in Garching, in the group of Benedetta Ciardi, and I was involved during my PhD, is still contributing to this code. Is a Monte Carlo 3D radiative transfer code, which originally was considering the propagation of radiation of hydrogen and helium ionizing radiation from 13.6 to 200 electron volts. And this was used to make first reionization simulations on large scale. So we are talking about 30 megaparsecs right now, okay? Studying the evolutionary redshift of the ionization fraction of hydrogen, helium. Now we are able to account for the metals, but this is not accounted in this picture. The gas temperature calculated self-consistently, tracking radiation intensity, and many other stuff. So in 2012, we published this first paper discussing the role of helium in hydrogen reionization. And what you see here is the redshift evolution of the volume average ionization fraction for hydrogen and for helium. The same plot is available for temperature in the paper. So the next step was to improve the chemistry of the gas and to include self-consistently metal ions, calculating metal ions and metal cooling in the gas by polluting the gas with metals and calculating the ionization states of this. So what you see here is the result we published in 2013. This is a filament polluted by metals. In each panel, you see C4, C5, C4, C3. All these ions are computed and calculated consistently with the radiation field, and we know finally the spatial distribution of the ions. So we have a way to interpret what oxygen-free means in terms of correlating it with the sources, creating it. OK, so the next version of CRASH focuses in extending this scheme first to X-rays. So we are implementing soft X-rays up to 10 kiloelectron volts. And we completely refactored and remodeled the code and to account for other bands like Lyman burner in the future. And there is one student right now working on radiative transfer through dust. But the approach of this code is that everything must be included self-consistently. So even this is really slow, we don't move from this direction, okay? Especially the secondary ionization was studied in great detail, trying to understand how different models of secondary ionization are impacting our results. So these are two applications we recently we are doing now. One is already published, is available in the archive, a project led by Koki Kakichi, and another one is in preparation. We are trying to understand what is the effect of a quasar I redshift on the surrounding environment first. So what you see here is isosurface of the logarithm of the temperature. The quasar is placed here, and you see the front at different temperatures. So red means hot, and blue means really cold. And this is the picture you obtain by including X-rays with respect to the picture you obtain just by stopping your radiation field at 200 electron volts. So the message here is that, as you can see, X-rays impact very large regions surrounding the quasar. This is a 25 moving megaparsecs, eating the gas and providing additional ionization, creating very large shells of partial ionization and heating. So once this is a picture in which a single quasar is put on a cosmic web, and you don't have the galaxies in background, but this is a little unrealistic if you want to, it's useful to understand things. But if you consider the role of the galaxies, moving to the second, to these plots, here you have three different columns showing a bubble, a region of ionized gas created by clustering of galaxies or around a single halo here. And when you will create this ionization picture, the three columns are three different emissivities models for the galaxies, which also are unconstrained, let's say. But by spanning different emissivities, you create this picture. You know where the galaxies are. You know what is the global picture. And once you power on the quasar, you can account for the concerted impact of galaxies and the quasar, trying to understand if the presence of the quasar changes the pattern, the ionization pattern, the temperature pattern. As you can see in the bottom panel, this CISO contour shows the pattern from the galaxies, and this is the increased, the increase in the ionization fraction and temperature produced by the quasar. So the presence of X-rays, especially I redshift, produce a sensitive impact. More details in the paper if you want. So that's another application. This is a very large scale, 100 megaparsecs moving. And this is a full reionization simulation starting at very high redshift. This is just one snapshot at redshift 8, in which galaxies only are considered. left and right, galaxies plus quasars. This is a very high redshift. You have a few quasars in this slice cut. How you can distinguish the role of the quasars here, look at the helium. Having high energy changes the status of the helium and changes the status of the temperature of the gas, but in regions surrounding quasars. So this simulation is running. We reach at redshift 6, so we can place a few constraints, and we will continue by studying helium reionization after. So the key questions of this problem is that, okay, we are able to do these simulations, but the nature of the sources is still unconstrained. We have to span different models. So what is the relative role of stars and quasars? What is the IgM heating if the presence of binaries emitting X-rays contribute? Can be solved, but don't forget that first, the feedback from radiation to star formation is not included in this scheme, and second, the nature of galactic sources is not clear. So we move to second problem, trying to understand the nature of these sources, okay? Trying to understand what is the chemical enrichment around these sources, trying to understand if these sources have dust, and if we can compute the right amount of dust at high redshift. Is not totally unconstrained as problem. We recently had a few observations providing up to upper limits. And look at this paper, which was really exciting, the detection of all three. So remember, we are able to compute these whole three. So finally, we could compare with something. I was really excited by that. And so we have to model these sources. We have to model the interstellar medium. We have to model the processes creating metals and dust. Let's try to do it. We tried to do it first with a semi-numerical approach, trying to place constraints, trying to understand the main processes at play, what is important. So I want to highlight these two papers done by Mattia Mancini, 2015, and now a recent paper. If you want more detail, have a look at this poster here and talk with Mattia. But the message is that with our semi-numerical models, combining a semi-analytical model for dust production and results for chemical enrichment from numerical simulations, we can form dust self-consistently with the star formation. We can account for supernovae contribution, we can account for AGB contribution, but if you want to match the upper limits, something else is at play. Some mechanism is increasing the mass of dust from the metals. So this is what we call grain growth. There is a large discussion these days about what grain growth is. I'm not going to define grain growth because I'm not able to do it, but other people are not able to do it anyway. But we need these mechanisms here. Once we have the dust produced, matching or consistent with the upper limits provided by simulations, we also try to investigate the properties, spectral properties of these high redshift galaxies, and this is the job we have done, trying to fit the luminosity functions, top panels, different redshifts, and the beta slopes of these galaxies. This was quite successful, showing that first, you need a multi-phase ISM model. Second, you need the right amount of dust. And you should know the distribution of the dust. You should know the structure, because this is only a semi-analytic approach. So the first step is to trying to put dust production in numerical simulations. So you can study the structure. Having a sufficiently high resolution, you can study the structure of this multi-phase ISM. And this goes into the direction of connecting chemical feedback with the radiative properties of these galaxies. If you know the structure, if from first principles, if you know the star formation, I'm not saying we are going to solve the escape fraction problem, but we are trying to understand what is the medium shaping this, okay? How many photons, ionizing photons, can escape from these high redshift galaxies. So we worked in this direction, including dust production in Gadget, creating this new version of Gadget based on Gadget 3, which is called Dusty Gadget. which, following a detailed stellar evolution based on the scheme of Tornatore 2007, accounting for contribution of supernovae, AGB, in non-instantaneous approximation, we can compute dust and metal production self-consistently, also including the effects of spreading by stellar winds. So this moves from chemical to mechanical to having an idea of the properties. This is the right in this plot. I show in the top panel the total amount of dust as a function of redshift comparing with the semi-analytic model. Okay, the agreement is quite good. They don't overlap because the semi-analytic model is not able to account for dust spreading outside galaxies. So there is a missing amount of dust here. But if you look at the evolution of the stellar mass, the two models have a super, super fine agreement. So, fine. We know how dust, we are able to simulate dust production in our simulations, but dust is more complicated. Dust evolves, reacts to the environment, okay? So there is dust lustration, grain growth, sublimations. So the step we are doing right now is to try to understand how these processes can be accounted. And this is a slide cut showing how our galaxies look in dust mass. You see this very irregular distribution of dust all around affected by winds. Okay, final step. We try to connect chemical and radiative feedback in a pipeline, connecting the codes. So we started from having a semi-analytic code, which is developed by Stefania Salvadori, by Rosa Valiante, approaching different problems. We connected with an embodied simulation. And if you follow the structure formation evolution along the redshift, and for each step, you can compute the galaxy, the stars, and the metal enrichment, transforming this into sources, propagating the radiation from the sources and back again for the initial conditions of the second generation of stars, you can find this picture here. So in this picture, I will show you, this is a different scale. This is a galaxy Milky Way galaxy formation scale, so it's around 4 megaparsecs. But as a gray pattern, you have the gas distribution, 3 different redshifts, 12, 9, and 6. And these isocontours are showing temperature isocontours. These bubbles are created by this filament, for example, of star-forming halos. And if some halo is trapped in one of these bubbles, and comparing the viral temperature with the temperature of the gas, we also implemented stopping of the inflow of gas and stopping star formation. So this goes into the direction of studying how chemical feedback and radiative feedback reacts and impact on star formation evolution. It's kind of late. Let me discuss this point, and I'll go through the conclusions. This is the star formation rate as function of redshift. For population 2 stars, red line, and for population 3 stars, because remember, we also have chemical enrichment in this model. So we can study how the transition between population 3 and 2 reacts to the radiative feedback. And as you can see, especially at high redshift, feedback matters in establishing the right moment for the transition in shaping star formation here, while the population 2. One thing I want to emphasize, in this model, this is the data constraint model, because the n-body simulation allows us to reach redshift 0 and match the star formation rate of the Milky Way. I'm done. So I cannot explain all these details, just emphasizing this. I'm sure Stefania Salvadori will discuss this in deep detail, the testable consequences of these models of redshift 0, studying the MDF of the Milky Way. So my conclusions are here. We try to approach feedback under different aspects and point of view. We have 3 tools, and we try to integrate all these 3 tools, and we are able to study the interplay between chemical, radiative. The mechanical feedback And the hydro is missing in our models, but is more investigated by our other codes. So I think it's more original from our side. First start from this point of view. Thank you very much.
Thank you. We have time for a few questions. Hans?
You emphasized a lot the role of dust. And you also, I saw on one of your slides, the effect of the reverse shock.
Yeah.
So what do you assume what the reverse shock is doing to the dust grains?
Okay, we have, I mean, this is not my work, and if you really want to understand more in detail this part, you should have a look at the poster of Stefania Marassi, who's modeling dust production from supernovae, accounting for nucleation, and also in the future will be, there are a lot of work done by Jones and Marco Bocchio, collaborating with us, implementing dust sputtering and the effects of a reverse shock in disrupting the dust produced by nucleation. So have a look at this poster, because it really is not my topic, and if you discuss with Stefania Marassi, you will have a lot of details.
But you do assume it survives.
Sorry again?
You do assume it survives.
I do assume what?
It survives.
It survives.
Yeah.
We don't assume it survives. We study the effect, I mean, the model, and I cannot discuss about the details because it's not my job. From my point of view, I want to know if you have, that simulation was megaparsecs scale. So what I want to know is that if I have a certain star formation rate, certain number of stars and mass of stars, I want to know how much dust is produced by the different type of stars. I don't think we totally assume that dust survives. I mean, we model the process. Maybe Stefania or Raffaella can provide more insights to you.
Raffaella?
So we do account for the partial distraction of the reverse shock, and the way we do that is to try to compare with the observations that we have in the present-day universe. And so we collected, the data that we have on different supernovae, and we ran our best fit model for the supernova progenitor, and then we try to match the observed dust mass at the age of the supernova remnants to date. So I think that this is the best that we can do for these models, for at least for the supernova dust sources. Oh no, it can vary tremendously. It also depends on the grain composition, because if you, as I showed in my talk, if you have predominantly small grains, these are more fragile towards dust destruction. So actually dust destruction changes not only the total mass, but also the composition and the size distribution.
Any last questions? If not, let's thank our speaker again.